Hello everyone, welcome to the Module-2 Session-3 of Discrete Mathematical Structure. So I am Professor Santosh here. So today we're going to discuss about the next concept of the Module-2, and I can say it's the next model of a mathematical induction. So in the previous two sessions what we had, so it was all about having a mathematical induction, so through which we are going to prove something out of 100 objects or out of n objects. I will just test few objects and I will tell that mathematically yes, this is going to be right or wrong. So now today we are just going to take one more variation of the same mathematical induction, so which we are going to call this as a recursive definition. And once the mathematical induction has been done, so now let us take the concept known as recursive definitions. Fine. So now what this recursive definition is going to be all about. Fine. So now whenever we are going to talk about, the recursive definition, fine, it's all about recursion. So we already came across what is recursion and how exactly the recursion is going to work with, but let me give an example and give more clarity about what a recursion is going to be all about. Fine. So if I want to put in a statement, the recursion, fine. So recursion is a process or a task which we are going to perform again and again, the similar kind of task. The number of objects what we are going to apply this task can vary, but the procedure is going to remain same with different set of parameters. And this is what we say the recursion is all about, doing the same thing again and again, depending upon or having a variable parameter size. Right? So now to give more solid example for this, let us consider a few fractals. So when I say fractals, it's a geometric shape, so which we are going to divide n number of times using a common procedure, and we end with an geometrical fractals. Right? So now, let me give an such example for you. So something called as Koch's snowflake. Right? So we are going to take an example of Koch's. So snowflake or snowflakes. Fine. So now to create the Koch snowflakes, what exactly happens here is I'm just going to take a triangle. I'm just going to take a triangle. Fine. So now this triangle is going to be equilateral triangle at this point of time. So for whenever I'm going to say n equals 1. So let me say n equals 1, that is at the point of first iteration. When I say n, you can consider this as one iteration, or at the first instance I'm going to have one equilateral triangle. So now what exact procedure what I'm going to use now, the procedure what I'm going to use here is to create a snowflake is, now whatever the line segment I'm going to have, to draw a triangle, each line segment I'm going to consider and I'm going to divide into 4 parts. Divide the segment into 3 parts, make it as 4 equal line segments. That is, so I am just going to have the same triangle. Now, equilateral triangle. So now the procedure what I am going to follow is I am going to divide this into 3 equal parts. Each line segment I am going to divide this into 3 equal parts. So once this is done, I am going to use the same line segment and I'm just going to create a triangle over here. So similarly, I'm going to take up this line segment and I'm going to create a triangle here. And similarly take up this line segment, the same size or same length of this segment, I'm going to create a triangle over here. Now this is what I'm going to do when I'm going to say n equals 2. When I'm going to have n equals 2. So now having this structure for n equals 2 or at the second instance or second iteration, now what happens at n3? What is going to happen at n3? Now during n3, now how many line segments I'm going to have? I'm going to have 1, 2, 3, 4. That is for every line segment I had previously. Each line segment now is going to have 4 line segments. Hence, I had 3, so 4 into 3. Obviously, I need to multiply this with 3 line segments, hence 4 into 3, I am going to get 12 line segments. So right now, there is going to be 12 line segments. Now for each line segment, whatever I am going to have, so let me just draw this and show to you. Right. Right now when I am going to have for N3, for each line segments, I am going to divide this again into 3 parts, and I am going to draw an triangle over it. So divide this into 3 parts, and using 4 line segments, I am going to draw a triangle over here. Again, triangle over here. So again, I am going to draw a triangle at this point. Again, divide this and draw a triangle. So divide this and draw a triangle, and divide this again and draw a triangle, and divide this again, draw a triangle, and divide this and draw a triangle. The same way I am going to do over here, and the same way I am going to do for this line segment and even for this line segment. Now this is what I am going to hang for n equals 3 or at the iteration number 3. Now what exactly you observed here? What exactly you observed here? Fine, the number of line segments is going to increase, but the procedure is going to remain same. I applied the same procedure of dividing a line segment into 3 parts and make it as 4 line segments and draw a new triangle, fine, or draw a new equilateral triangle. And so now the same procedure was applied on these 3 line segments. The same procedure now had been applied on these 12 line segments. Hence the procedure remains same. So repeating the same task again and again on a few objects or n number of objects, it is going to depend how the recursion is going to work with, or this is what we are going to call this as a recursion. Right? I hope you are clear with this recursion. So now this recursion I need to put into form of a definition, or I want to define this recursion in form of an equation, in form of a statement. So to do that, we just look at this. So now if I am going to say how many sides this is going to contain, how many sides this particular structure is going to contain, is the number of line segments. When n equals 1, I am going to have 3 line segments. When n equals 2, I am going to have 12 line segments. And when n equals going to be 4, if you want you can count, it is going to be 48 line segments. So in general, how do I write this? Fine. How I am going to write exactly this, or I need to count and I need to generalize what exactly this is going to be. So now, if I want to know how many equilateral triangles, every time I am going to put into how many equilateral triangles I am going to have in this particular case. Now when n equals 1, there is going to be one equilateral triangle. Or if I want to know how many line segments each is going to contain, so let me generalize this for the number of line segments, then we'll go into number of equilateral triangles at every iteration. Fine. So now if I want to know how many line segments is going to contain, now I'm sure that whenever I'm going to create a new iteration, I'm going to introduce a new equilateral triangle. Fine. Hence, so every equilateral triangle or every line segment has been divided into 4 line segments. Hence, I'm going to have 4 line segments. So now I'm dividing the line segment. I'm not dividing the line segment at this point of time. Hence, there is no division. Hence, I will just say 4 to the power of 0, and I'm going to multiply this with 3. And so 3 into 4 to the power of 0 is 1. 3 into 1 is 3. Hence, the number of line segments or number of sides is going to state 3. The same, now I'm going to divide the line segment. Hence, I'm going to have 3 into 4 to the power of 1. And this is going to be now 3 into 4 is 12. So similarly, you can guess this what it's going to be. So 3 into 4 to the power of 2. And the similar way I can do for n. I can just check out what the n is going to be. When n equals 1, this is going to be 4 to the power of 0. N equals 2, 4 to the power of 1. N is 3, 4 to the power of 2. And so now what in general this is going to be? This is going to be 3 into 4 to the power of n minus 1. Fine. If I give what's the value of n, now you can easily say how many line segments or how many sides this structure snowflakes is going to contain. So now if I want to know how many equilateral triangles this is going to contain, so what I'm going to do is, I know what is number of edges or segments each equilateral triangle is going to contain. It's going to be 3. If I divide these values by 3, hence in general, the formula what I can use, so 3 into 4 to the power of n minus 1 divided by 3 is going to give me number of equilateral triangles. And so let me put this number of equilateral triangles. Now how many triangles it's going to be? Now I need to divide this by 3. If I divide this by 3, I am going to end with 4 to the power of 0, comma, I am going to have 4 to the power of 1, and so on. I am going to have 4 to the power of 2. So in general, as I already mentioned, this is going to be 4 to the power of n minus 1. This is the number of equilateral triangles what I am going to have. Now just observe here. In the first iteration, we have already one equilateral triangle. In second iteration, if you carefully observe, I am creating 3 new equilateral triangles. And the one equilateral triangle already existing, which is carried from the iteration 1. And if I go further, so there are already 4 equilateral triangles, one carried from the iteration 1 and 3 newly introduced. Fine. Now this 4 will be carried out here, and so there are new 42 triangles or 44 equilateral triangles, including the 4, which becomes 48. That is what, at the iteration 1, I am going to have 3 sides, but I am going to have 1 equilateral triangle. In this case, I am going to have 4 equilateral triangle. So in this case, if I am going to divide 48 by 3, I am just going to end with a value. This is going to give me number of equilateral triangles. So now I need to sum up. So now I am not going to wholesale depend upon number of equilateral triangles what is going to be. It depends upon the previous one which I am carrying into this. And for this case, instead of putting the form in this way, I am just going to put this as, at the starting, I am going to have 1 equilateral triangle which will be carried to the next iteration. In the next iteration, I am going to have 4 to the power of 1. I am going to have 4 to the power of 1 equilateral triangles, but I am already considering 1 equilateral triangle here. Now this will sum up to 5 equilateral triangles, but here there is going to be only 4 equilateral triangles. Hence that case, the previous value I am going to subtract this with 4 to the power of 0, plus I am going to find how many equilateral triangles are here, and I need to subtract the previous equilateral triangle. So it is 4 to the power of 1, and plus so on. I am just going to end up this as 4 to the power of n minus 1 minus 4 to the power of n minus 2. Now just observe here, the previous iteration data has been carried to the current iteration. So this is how the recursion is going to put in the form of an equation. And now whatever the form we are writing here, in general, whatever the equation we are trying to derive to find the number of equilateral triangles, to find the number of segments, or to find or to have the previous equilateral, and if I want to tell the total equilateral triangles, This is the general form of equation what I'm going to put into. Fine. So now this can be a recursion, or this can be any sort of operation. This can be put in the form of a general equation. And now whenever you're going to have general equation, you can represent this general equation in two ways. Remember this. Whatever the general form I have been putting into to compute the number of sides, the number of segments, the number of equilateral triangles. So this general equation I can put in two forms. So in mathematical induction or in the discrete mathematical structure, I can represent a general form in two ways. Fine. So remember this. So this is where our discussion will be carried forward. So the first is going to be the explicit way. The first one is going to be explicit method, and the second is going to be recursive method. So these are the two methods which I can make use of whenever I am going to represent the general form of equations. Fine. Hence, I am going to have explicit method where I can have a general form, and I am going to have recursive method where even I am going to have a general form to be presented. Fine. So now I am just going to give an example and clearly make you understand what or how we are going to represent using an explicit method and how we are going to represent the same equation using a recursive method. Now, whenever you want to represent a recursive definition, fine, that is the recursive method what I am talking about. So all this time, knowingly or unknowingly, we were using explicit method. The mathematical induction problem in the previous session, whatever we came across, that was the equations where we worked the general form in the form of explicit method. And now we are just moving a bit ahead so that we are going to represent something in recursive method or in a recursive form. Fine. So now for that case, now whenever you want to have this particular recursive method or explicit method, so it is sure that I need to have a set of elements. Something like I am going to have the element 1, so which I present this as A1, and I am going to have A2, and I am going to have A3, hence I am going to have n number of elements. And in general, I can present how these elements are related with something like sum of n natural numbers, which I can present as 1 plus 2 plus 3 plus so on, n equals 1 by 2 n into n plus 1. That is how we are going to put set of elements in some form. So in some discussion or in some form of context where you may refer, even they may refer the set of elements starting from a of 0 and they will reach to a of 1 and so on until a of n minus 1. But for our discussion, we'll always put the first element as a of 1. Fine. But in some textbook which you may refer or some other source, they may refer the first element as a as 0, but still it's only the way we are going to denote. But so we can put into common terms so when we start discussing. And so now we're just going to consider the A1 as the first element and so on. So now whenever I want to define this using recursive definition, this set of elements, so now we'll just take an example where we are going to have list of elements, something we say E. So the set of elements which we are going to call this as E, and I'm going to have this as set of n elements. Now how we are going to fill this, or how we are going to have this set of elements. Now what is the rules? Depending upon the rules, if any integer is going to satisfy the rules what I am putting right now, so that particular integer should be part of this set. If it is not following the rules, or if it doesn't matches the rules what I am putting, so that should not be in this subset or in this set. So now the rules what I am going to talk, the rules what I am going to put, or I can say depends on rules. Now the rules what I am going to put This rules is called as description or general description, and I told you the general description can be in form of explicit method or it can be in the form of recursive method. So now, for example, now this set, whatever I'm going to have, I want this set to be filled with even integers, even positive integers. That is, I want this set to be filled with positive even integers. Now, what's the rules I'm going to follow in this case? What are the rules I'm going to follow? So now, if I'm going to follow the explicit method, the rules what I'm going to put is, now whatever the value I'm going to take, that is the object an should be equivalent to the multiple of n, hence 2n, where you need to make sure n is going to be a positive integer. Hence, the n should always belongs to z plus. So this is the explicit method. So I'm just going to give a value of n. If you give any value of n, so that is going to be multiplied with 2, and as we all know, any number which is multiple of 2, it is sure it is going to be an even number, and it follows the rules and it should be part of the set. So this is how we are going to present using explicit form. So let me put this as 1 so that you will understand this is going to be the explicit method. So now, if I am going to talk about this next method, that is the recursive method, how do I do this? Now just understand, whenever you're going to have a recursive method or recursion, you need to have few concepts which you need to use. So without those basic concepts, you cannot move forward. The first basic component is, for any recursion, it should have a base condition or it should have a base value. So without the base condition or the base value, I cannot move on. Fine? And I need to have from where the recursion should start and where the recursion is going to stop. At some point, the base condition can help me to stop the recursion, or else if there is no base condition, the recursion will go for infinite iteration or infinite steps. Hence, I need to have where I am going to start the recursion and where I am going to stop the recursion in form of a base condition. Along with these two, I need the rules. The rules which I need to follow or the procedure which I need to follow so that I can carry out. Fine? So hence, so for that case, the very first thing is I need a base condition, that is the very first element a1. I should mention explicitly, I need to mention what is the value of a1, and now this should be a direct value. So I need to mention what a1 is going to be. So initially, we know that the very first positive integer even number leaving out 0 is going to be 2. Now this acts as my base condition. Now what the rules I have to follow here is an should be equivalent to, now this should depend upon the previous element. So if I just keep on adding by 2, that is going to give me an even number. Hence, I am going to have 2. So for this 2, if I am going to add 2, this is going to give me 4, which is going to be an even number. Hence, now where this 2 has been stored? In a1. Or I can say it is the previous element. It's going to be the previous element is a of n minus 1. Now if I want to compute what is a2, a2 equals a1 plus 2, where a1 is 2, hence I will end with a1 equals 4. Similarly, the a3 will depend upon a2 value, add with that and put it as 6. This is the rules what I am going to make. So now what's the, from where the recursion should start? So should this n start with 1 or 0? If n is going to start at 0, if I am going to say n is 0, as you're trying to find a0, but I said my discussion will start at a1. So where is a0 element? So hence I cannot start n with 0. So what if I am going to start this with 1? a1 equals 1 minus 1 becomes 0. Now what is a0? The base condition or the base value itself will start at a1. Hence I cannot use n as 1 also. Now what if I'm going to use n equals 2? If n equals 2, then a2 equals a1. Now this works perfectly for me. Now this is the point where I need to start my recursion. Hence, along with these rules, we'll just say for n is greater than or equal to 2. Now this is what I need to make use of whenever I'm going to talk about a recursive definition. Now just look at this. I'm going to have an equals 2n is in general form. And even an equals an minus 1 plus 2 is a general form. This is in the form of explicit. So when it is explicit, it doesn't depend upon the previous value. That is what in the snowflakes example I had put you. So whenever you want to find the number of segments or number of equilateral triangles for a particular iteration, I need not depend upon the previous. But if I want to count the total number of equilateral triangles, I need to depend upon the previous value. Hence, so if I want to explicitly mention a value, I'm just going to directly compute what is the value for a particular instance of iteration. That is n. If you want to depend upon the previous values and work on the current value, so being at the previous, if I want to work on the current value, or if being at the current value, if I want to work on the next value, in that case, think about recursive general form. Fine. So this is how we are going to present a general form using an explicit method and using a recursive method. So now, whenever going to have this recursion method, so in explicit method, it is just as I am putting it as in explicit way. But whenever you're going to talk about a recursive method, what you want to watch out here is decide what you're doing now. That is, so being at the current element, or you finding the next element, or if you want to find the current element, or you depending upon the previous element. Being at the current element, that is n, I am depending upon the previous element to compute the current value. Then this equation will stay good. Now, being at the previous element or being at the next element, I want to compute what the current element is going to be. In that case, I can represent this as an plus 1. That is, so being at the current, I am trying to find the next element. In that case, an plus 1 equals, this should be an plus 2. So fine, or else, so if I want to compute the previous element, that is n minus 1, so this will be equivalent to, so n plus 2. Now this is how you're going to put the forms into. So it's supposed to be n minus 2. It's supposed to be n minus 2. Fine. So this is how exactly you're going to decide. So now either being to compute the current element, I'm depending upon the previous element. And this is always also equivalent to I'm computing the next element being at the current element. Fine. Or I'm going to compute the previous second element being or computing or using the previous element. So all these three forms are similar, but depending upon this form, even this starting of recursion should change. Now what the value of n should be for this and what the value of n should be for this. So just think and try to fill out this particular equation or for particular form. Now this is what the explicit method and recursive method is going to stand at. I hope I am clear with this. I'm clear with this, and as I mentioned, now this is going to be called as the base of the recursion or the basis of a recursion. And either this form or any of this form, we call this as a rule or we call this as a recursive rule. We call this as recursive rule. Fine. So now this is what explicit method and recursive method is going to be. Now let me take an example, because whenever we are going to solve a problem on this, so if I'm going to give something in a form of explicit, you should be able to convert this explicit form into recursive form. Or if I'm giving something in a recursive form, you should be able to convert this to an explicit form. Fine. So we'll see how exactly this has been done, taking the same example. So I'll just show you how exactly this should be converted, or this should be carried out to this form and this to this form. So we'll just see. Fine. Now just taking the same example, that is where I need to fill out the list with the odd numbers. Fill the odd numbers. The rules what I am going to use, the explicit rule what I am going to use is, I am going to have an element, that is an, so which is going to be 2 into n. So it is going to be an equals 2 into n, where n is going to belong to the positive integers. Fine. So now I am going to have this as an explicit form. So this is being an explicit form. I need to show how I am going to represent the same using a recursive form. So for that, I am going to now just find what is a1 is going to be. So what is a1? So a1 is 2 into 1. This is going to be 2 for me. So now what is a2? Just compute what is a2. a2 is going to be, so 2 and n is 2. This is going to be 4. And what is a3? a3 is going to be 2 into 3, that's 6. Hence, I am going to end with a1 is 2, a2 is 4, a3 is 6, and so on. So it will go on. So when do I stop? It depends upon what the n value I am going to give. So now, having this value, now just find what is a1 and a2, or I can just say a2 minus a1. Just find the difference. So a2 is 4 and 4 minus 2 is going to give me 2. So the difference is 2. And even if you just look at this a2 and a3, so a3 minus a2, that equals, so a3 is 6 and a2 is 4. And again this will be 2s, so I am going to have a common difference between this set of elements. So now what I am going to do here is, now just find how to find a2 here. So now I will just remove this particular form. Check it out later, this will work for a3 also. Now a2 equals, I will just shift a1 over here, and I will shift a1 over here, and I am going to have plus 2. So a2 equals a1 plus 2. Now this a2, if I want to represent for a3, so a3 will be equivalent to a2 plus 2. If you want, you can just check it out. Fine. So similarly, this will go on until an, which is equivalent to, if it is an, this is going to be equivalent to an minus 1 and plus 2. So now, for this is going to be the recursive form. This is going to be the recursive form, and this is the recursive rule. Now, what is the base value or the basis for this? That is going to be the very first element, that is a1 equals 2. So from where I need to start to compute the recursion, that is I am going to have a equals 2, because already I know what is a1. Now I need to find what is a2. Hence for n greater than or equivalent to 2. Now this is how I am going to convert. So from the general explicit form to a recursive form. This is how I am going to convert. Is it fine? I hope it's clear for you. So now I'll just show you. So for a given recursive rule, I need to convert it to explicit form. How I'm going to do it in reverse way. So for that, so let me put it in a reverse way. So where I'm going to remove this explicit form. So for that, the very first base condition is I need to know what is a1. So I will just say a1 equals 2, as all we know. And the general rule is an equals n minus 1 plus 2. So for n is greater than or equivalent to 2. Now this is a recursive form. Now I need to convert this to an explicit form. So to do that, I am going to consider this an. I am going to consider the rule an equals n minus 1 plus 2. So now just observe there is an an over here. There is an an over here. So I know what is an, and I need to replace this an with what I know at this point of time. Hence, now if I am going to replace an, so what is an? An is an minus 1 plus 2. Yes, now just replace only this an now. An is, so an minus 1 plus 2. Fine. So I am just replacing this an with minus 2. And so now this should be minus 1. So plus 2. This should be minus 1. And this plus 2 should be taken as it is. As I am going to have this as plus 2. So I am just replacing an with an minus 1 plus 2. This minus 1 remains as it is. And plus 2 will carry it out here as it is. So now if I simplify this, I can just say this as an. So if I just simplify, I'm just going to have this as an minus 2 plus 2 plus 2. I hope I'm clear. So now again I should replace this n. So if I replace this n again with an minus 1 plus 2, so as you can understand, this will stand at an minus 3 plus 2 plus 2 and plus 2 will be carried on. Fine. So now this is what I'm going to go through this. So just to simplify the same statement, I can put this as n minus 3 plus how many times? It is 3 into 2 or 3 multiplied with 2 for n minus 3. So on. If I keep on going, now where do I stand it, or where should I stand this value at? So now can I make this as an minus n? If I make an minus n, if I go until n, this will be a0. But in our recursive definition set, as we have came to a conclusion, so we are now going to take a0. We'll stop at a1. So to make this as a1, I need to add this as n minus, and take until n minus 1. Hence, I am going to have n minus of n minus 1 plus, just observe, when it was 2, I multiplied 2 times. When it was 3, I multiplied 3 times. So same way I need to multiply how many times? That is n minus 1 into 2. Now this is how I am going to represent. Now to simplify this, just simplify this. This is going to be a. So n minus n is, it cancels each other. So minus of minus is plus. And so a1 plus n minus 1 into 2. Now what is a1? So I know from the basis condition that a1 is going to be 2. And so replace this with 2 plus n minus 1 into 2. So just take 2 common, 2 as common. So 2 of n minus 1 plus 1. So 1 minus 1 plus 1 gets cancelled, and I'm going to end with, I'm just going to end with 2n. I'm going to end with 2n. Now if you just observe, I have ended with 2n. So now as per the explicit form, so an equals 2n. Now this is where, so from the recursive, I have converted or to an explicit form. Now this is how, by resubstituting recursively, if I recursively keep on substitute, so this is what I am going to end with. And this is what exactly I need to understand by the recursive nature. And so now we'll end this session. But remember what do we mean by recursive definition, and how exactly the recursive definition should be used, or when should be used. That is, for any given objects which I want to put in a form of a statement or form or in a formula, we are going to have a general form. And the general form can be put in 2 types, the explicit method and a recursive method. And you should know what is explicit method and even understand what is recursive method. And along with that, make sure you understand what is or how we are going to convert an explicit method, that is an equals 2n, to a recursive method, you should know both the ways. Fine, and you should know how to convert a recursive form into an explicit form. So now please try out these problems, which is similar to what I have just done. In the next session, I will help you out in solving this, understand this problem in a better way and with few more examples. Thank you for this session.